Welcome everyone for the Cloud Computing and Big Data course. We have lecture 6 today, Deep Learning driven by Big Data, and that's the second course part. In the first course part, we had the basics of neural networks, essentially starting with a neuron, which, so to speak, is implemented with a perceptron idea that we already learned in lecture 2. We extended this idea with a linear learning model of introducing non-linearities as activation function, and have seen we actually can improve our modeling by starting maybe with the output perceptron, multi-output perceptron with 91% up to neural networks, which seem to be going to 95% in this handwritten character recognition. So there is something to the architecture. Obviously, as we have already discussed here in the break about our brain, we are the best supercomputers, right? So think about that all of these connections that you have seen in the video need to be computed. We human brain people can do this incredibly performance-wise well, which you think about in computing means lots of matrix vector multiplications again and again, weight input data, weights update, input data update, etc. We talked about epochs in the break, so that means you do it epoch-wise. In the epochs, you have seen there was a batch problem size, so we basically put that into different batches and then do weight updates. Long story short, lots of computing. We also seen basically in the first part that we had this 2D problem, which was basically then this grayscale image, right, with 0, 7, something, vectorized. We call that vectorized when we put that from a 2D in a 1D, for instance, representation. No rocket science, but we're losing spatial information. So our pixels around it will be lost if we put it to the neural networks. Right? So that gives us a thinking, maybe there could be something improving that situation if we keep the spatial connectivity, right? This is a very important part in our research called remote sensing, where you have land cover on a pixel-wise. Some of you take the course from Gabriel, right? I think, Gabriel Cavallaro, right? Then you know perhaps what I'm thinking about. So one pixel, if there's a water pixel from a satellite image of a city, it suggests that nearby might be also a water pixel and another water pixel. So this information can help us potentially to actually classify the whole story much better. And that is basically where convolutional neural networks are good in, which is basically today more or less a trivial learning model, but captures nicely the essence of the spatial connectivity. So that would be our second part. And by this, I want to give you a concrete deep learning method or technology at hand, which is, of course, let's say not the cutting edge model like transformer models we do in research right now, but it captures the essence of deep learning. And in many ways, one of it that we learn basically to think about that is not only just deep layers, also each layer has a special property, and that's what we will learn with the convolutional function and feature maps. So let's have a broader look then, basically. Deep learning is today used everywhere successfully, has surpassed basically computer vision algorithms by far these days. So it's a modus operandi in science and engineering for almost all problems that you have related to AI, for basically getting natural language out of vision. We have basically probably heard from the AlphaGo, right? Basically this interesting neural network that beat the champion. For us in science and engineering, it's interesting that the first neural networks have basically captured physics in flowing. So even unknown, basically, objects for fluid flow can be trained and learned. It was largely a problem because of turbulence and so on, or many factors in engineering, which we solve more and more. Obviously, there's still a couple of problems left, but the basic flow can be learned now. And that's a quite interesting property. What we look, for instance, in the RACE project. Right, so the RACE project is an AI project where I'm working in currently in research, and we have lots of these engineering problems from CFD, a field called computational fluid dynamics, where we look at these interesting aspects. So there's news in all sorts of places, and you can go on to protein folding. You have seen basically AlphaGo was transferred to AlphaFold, basically also doing a very good job in protein folding. And this is all true to deep learning. Right? When you learn these models, which are more or less cutting edge, you really need HPC and clouds. And for the simple ingredients, we just seen that basically it's a lot of matrix multiplication or matrix vector multiplications. We come to the details a little bit in lecture 7 more, right? Where I will explain then more in detail the deep learning architectures combined with GPUs, why GPUs are so brilliant for basically these problems. But if you now look in cutting edge models, we give lots of trainings. And if you're interested to learn more, as I said, I'm not a deep learning course here, but we teach a lot of this in our RAISE YouTube channel. If you want, monthly, I do their trainings on transformers, graph neural networks, very nice property. Also preserving the spatial connectivity in terms of connections to people or to objects or whatever it is. So also a nice topic. Autoencoders, very interesting topic to basically learn a latent space of some properties in data, which can help you to interpret a little bit what the learning is about. So you go on and go on. These neural networks basically today, in terms of deep learning, are highly successful, but also require more and more professorship on its own. So I think these days we're at the time where it's not enough to teach a deep learning course. We need basically now professors in deep learning and teach a course on transformers, course on autoencoders, and so on, right? So there's a new paradigm where we also talk about in the faculty how we extend this. So obviously this can be integrated in some of the physics models. We talk about surrogate modeling. That's one of the research aspects we do. For instance, a wind farm today, we cannot really model in physics with CFD. It's too computationally complex. But what we're starting is from a whole wind farm to do surrogate models of one wind wheel with AI, which is computationally sound. And you combine some of these models with physical models and machine learning models. But this is more research where we are right now in cutting edge research. Still, the basic ingredients in all of these models is what you just have seen. The neuron is still the basic building blocks. The question is how you arrange them and what is now the added value of all these different models, right? As I was alluding to, I think in one of my earlier lectures, it's not just deeper layers and lots of neurons that we have seen in the video. Each of these models has a specific property which makes it so successful. Bridging to the course. So why are we teaching this as part of the cloud computing and big data course? Why cloud computing resources are necessary is basically, again, this graph. I showed it already in the prologue. I think if I remember that if you have shallow learning models, so this neural network that we have seen with 2 layers, all random forests, support vector machines, all of these, let's say, traditional models, and you have, let's say, big data, then you're in trouble from the memory perspective, but computationally, you should be still okay here and there. If you want to have big data, then you basically start to being in problem because your memory on the laptop will not work. Oops, what was happening here? Okay, magic. But it's probably because I put the emphasis on the error here. But essentially, when you grow up, then do small neural networks, starting adding more hidden layers, you still have the same effect. You basically grow in accuracy. And with a laptop, you're still okay. The more you enter big data, really large petabytes, terabytes of data to learn from, your laptop will not make it. Simply because of the epochs, all of the data, it basically is at the end of the memory. So if you go up and go up, you will see medium deep learning, like maybe the convolutional neural networks that we see today. This is CNN. You're already in the medium space. You will see the computational footprint more and more in terms of computing power needed to learn these models quickly, or to basically catch the data into the memory, because memory is very, very limited, as we know from one of the earlier lectures, right, on many cores and multi-cores. So basically, this is something where we now start to combining many, many different nodes that you see here in terms of GPUs and CPUs. Now, GPUs have a very specific role to play in deep learning success. Without GPUs, or basically this many core architecture, we would have not success with deep learning. And one of your assignments will be to find that out. Basically, CPUs and deep learning doesn't work well together. It's too slow, and a transformer model, which is cutting edge in basically vision or so, then you would basically spend years on your laptop, but before it will break anyway, because it needs the necessary data. Hence, HPC and cloud computing is necessary more and more. Just a connection here, the Nobel Prize in Computer Science, as it is sometimes called, right? The A.M. Turing Award here was also going then finally to this deep learning people that invented it, Hinton and so on, and Yoshua Bengio, etc., because it was really a success. 10 years ago, we as machine learners were not convinced on that, right? So it had to take time, because many people are saying, oh, that's a hoax. People had the idea in the 70s. But combining it with GPU power now, having the power to compute all of this in real practice, we had major success. Now, the other end of the scale, if you want, now are we there that we can model the human brain? Can we do GPUs without end? Basically, we have big computers, we have high performance computers with thousands of GPUs. Here we go and have basically also some inputs here from our RACE project. You can combine more and more GPUs. You see here on one of our computers, we do 2048, basically on a computational fluid dynamics problem. And it's sort of really nice ideal speed up. So it's actually getting faster and faster, very nice. But then suddenly there's a significant drop in efficiency, what we don't want. So the GPU is not anymore filled. And that is because we have to still basically have the averages of the weight updates and the gradients distributed. This is something which Rocco will explain a bit more in distributed deep learning in lecture 7.1, and I will allude to also already in lecture 7. But there, let's say, are technical limits so that we not can scale up to the whole human brain and solve any machine learning problem. Hence, computing is good, high performance computing, cloud computing, you can speed up significantly. But we are not there yet that AI can be just, forever perfect as our human brain of connecting just more and more and more. In the end, we will run in this problem of having, that at some point in time, the GPUs are not actually there yet from the technology. And this has certain roles, HBM, the memory, basically it has to be fueled from the host CPU. Lots of factors I will explain in the next lectures. Hence, let's look a little bit more what we basically learned now in this deep learning. One of the things is basically the key, let's say, difference we had already discussed a bit was basically in former times, we have put lots of feature engineering, feature preparation into deep learning networks. You see that here, that has to be manually done. And basically we learned a model. That's more how you did traditional machine learning. Now, the interesting news with deep learning is, and basically on different levels, CNN will be here good on the spatial aspects. Transformer models will have a representation learning. So all of them have in common that they learn features, that they basically learn the data by themselves and not we humans do that. And this, of course, has some properties where we humans never think on or basically don't have the capacity to do that on scale, like, of course, transformers and other models can do that. I just repeat here a little bit the kind of deep learning / perceptron idea, again, for you to now contrast these models. So that's where we started, neural networks, basically with a simple perceptron, right? That's where lecture 2, essentially. But now we extended this to multi-output perceptron that's needed to not only say +1, -1, but to have a digit. So we had 10 outputs. Still one layer, right? No big hidden layers, just one output layer. We had a softmax for this to do the probabilities. That's what you see a little bit the points here saying probability of 7, 8, 9, etc. Now then we extended this basically now to this neural networks, which were just the idea of putting now different of those neurons next to each other in different layers, right? And this gave us this multi-layer perceptron, or also artificial. So the ANN, as we call it, as a fast feed forward different architectures, how we can model it. But the key message is also, it still has this kind of 1D input we discussed, which means we break any spatial context. You can incorporate this with feature engineering. So some people have another feature called symmetry, or another, which is obviously something for digits to understand. But this would go too far. Now, and here is basically a good illustration of what we do now in deep learning. So this convolutional network will learn the numbers not anymore just layer by layer, but will also preserve the spatial 2D, right? With the convolutional aspects of different features, but preserving the 2D architecture basically of the input image. And this is also true for 3D. It can do the same thing for 3D as we see. And now, because we had a break, we talk about what we say as a limit. The humans, they create new connections. So this will be the next one coming, called spiking networks. The problem in neural networks is we are bound to one architecture, but we humans create new connections. That's what we not can do, basically, in typical networks. So this is also cutting-edge research, computationally quite expensive. We're not there yet to teach that. But of course, this would be towards more modeling the human brain. Great. Hence, for you, the takeaway message is deep learning is not just this. It is very important for you to realize, right? It's not just putting more neurons layer by layer by layer, and then you're done. It's not like a neural network architecture. It's basically a complete different idea of putting basically feature extraction, feature learning, representational learning and transformers into the game, but then do basically a traditional classification scheme maybe on top of it. Things like transfer learning are possible. So lots of different angles how you can learn from a model, and all of them would be different lectures in a deep learning lecture that you basically can enroll if you want. The power of this is that you think not any more signal by signal, so to speak, but you capture features. And what you see in features is essentially when you see the human pictures, right, a face, it will not learn the face anymore, basically pixel by pixel or so. It will gain several features like eyes, ears, noses. And then on different layers, you will see it breaks down to different lines, corners, small features that basically are learned that incorporate the whole model. Still, as you see here, nicely, the 2D is preserved. Now, what we assume now for our handwritten character recognition, that means 100% performance. What do you think? I told you before, machine learning can never be 100, right? It's a bad question. And why we can't do 100? Because there would be always noise in the data, right? So these are actually out of the data set. And here's a question. Now, what digits are they, right? So basically, I said to you, sometimes rubbish in, rubbish out. A machine learning system has no chance to make it perfect if, let's say, so much noise data is coming in. And this is just one of the reasons. Another one is basically also the complexity of the data set, things we basically would cover probably in the machine learning course, right? Hence, we thinking about now by preserving the 2D spatial relationship, we can improve. But by seeing some of these dirty samples of data, as we call it, we cannot do 100%. And now let's prove that with deep learning. And step by step, how we basically incorporate this now with this feature learning or this feature maps. There are different concepts to it, and this is now one of the ideas why I say not neuron by neuron by neuron, right? Here we're thinking about basically now the first idea of going through the data set, but by preserving basically with a window and with a perceptron, like we learn basically with a perceptual layer part, the spatial connectivity. How big that is a hyperparameter you have to choose, right? So how much you basically want to have by striving over this input. Right? If you think about how we did it with the neural network, we took every of these input neurons in one long layer, signal in, learn, signal in, learn, right? One layer, so to speak, at a time. So what here is the difference is we get of going with this kind of receptive field like humans do, right? If we identify a car, we go over the car and identify a tire. The tire, okay, that might be a car. That's how we humans work. We don't go pixel by pixel over a car and think, yeah, maybe all these pixels match together car in my mind. So we learn features and we identify feature for it. And that's the same idea. The perceptual field will be learned basically with our vision. So of course, obviously, the features could be differently implemented or interpreted. Hence, we have so-called different feature maps. We can also configure how many we want to have. And I have a nice illustration on the figures of the characters to show you later. This is now a little bit dry. And of course, when you do it in practice, you will see it a little bit. And by then, basically do a so-called convolutional filter operation on this, where then also the learning takes place. So we go over this basically step by step, as you see here, basically always with this kind of receptive field. Go by it, and it will allude to just one basically connection to the next layer, and then basically to the next neuron and to the next. I think the idea is clear, and it's nicely actually shown with this graphic here, which is a smaller toy problem, but it captures the essence. So what the machine learning is just doing here, or the deep learning where now the computing comes in, it learns a filter that basically applies here in this 3x3 setup, a certain filter scheme for multiplication again. So where you basically come then to these numbers, where you learn a certain representation of the data. It's a convolved feature, as we also sometimes call. So how big the filter should be, how the striding is, how you basically move through this are all hyperparameters. You also basically have to think to check. Hence, hyperparameter tuning also needs cloud computing, because once you do a CNN, it's very fixed on that architecture. you cannot change it, but with the hyperparameter optimization, you change these things. So basically later on, you will be having a filter size of 5 by 5 because the filter on 4 by 4 to capture the features was not good enough. But this is only something you find out by changing these hyperparameters. And why it's so successful? Because basically you learn now, as humans do, on basic features that also preserve the 2D. And now you can imagine we are more complex than this. Our world is not 2D, we have 3D. Basically in Gabriel's course, you go in 200D with spectral channels into the Earth, right, from the satellite. It has basically spectral, multispectral or hydrospectral layers where you have 200 dimensions. For a simple illustration of an image, you know the RGB model of the image, right? So red, green, blue. This is already 3D, which you can incorporate in the model. And that's how you can see, is this working also for multidimensional aspects? So, and that's where actually also the name tensor comes from, which stands for multidimensional aspects in terms of higher than a matrix. And what you're essentially doing is then you create this filter, here a 3D filter now, basically to create this feature maps. And this are learnable weights, things you already know, the red things. This is something we have to learn, right? So this is again, nothing else than the connections we had before with the neurons. So we have to learn it, but we have a very specific way of doing it. And we can configure now how many feature maps we want, which means we multiply the number. It's not only anymore one connection to each layer, so also to the feature maps. However, there's something called weight sharing, which we also allude to in the next concept, which makes it a bit simpler. So we don't have a dense network anymore. That's good because we want to have features here basically learned as a complete receptive field, right? So hence the idea of this weight is shared because sometimes the car, tire could be more on the right, on the left, maybe above even with a car that was crashed, right? So basically we want to have something called location independence with these features to learn, which we achieve by this, especially by having this basically in this feature maps and then with weight sharing. So over this, we have still, of course, the kind of architecture of having layer by layer by layer. So not doing it once, this convolution operator and learning a feature and basically this filters we discussed, where your weights come in, you learned before with the neurons, but now on a much more scale. We do this again and again and again. And this is where this ResNet 50 or these ideas of 50 layers come from. So here you have a very simple AlexNet, one of the first initial CNNs, very simple, not what we use in research, but it's still good enough to have a car recognized or image recognition doing something like this. And the way it learns basically is by always doing this convolution operation, then the rectified linear unit. So this stays, the non-linearity, of course, pro neuron, and then basically apply this again and again. There's one concept I also want to allude to is the pooling. We can have max pooling, average pooling, which means a sort of reduction of the data significantly, because if you have more and more higher level images, it becomes quite computational complex, as you can imagine. For instance, if you think pixel by pixel, that's what I said in the beginning, right? Now putting a big iPhone picture in HD, big super duper format is infeasible for computing. If you would now process it neuron by neuron, what you rather do is you subsample, so to speak, on the strongest signal. For instance, like max pooling. So the max pooling on a 4x4 maybe part, just the maximum will survive, or average on all of this. And we will come to these concepts again and again in this lecture, in lecture 7, Rocco will allude it in lecture 7.1, right? Admittedly, it's just a simple start of this. In the end, we still have the idea of performing classification, right? So now we put all of that, interesting enough, with features, and now again vectorize. But now we have a very significant idea what these features are, and we put that basically in the softmax that you see here, in a fully connected network structure. Hence, the neural network that you already know, the dense, fully connected network, is basically just behind, put on top of the feature learning, right? And this is the difference now to neural networks, essentially. While the neurons here had to do the full job, here we learn features for the neural network, apply it in the neural network, and do the softmax of probability. It's a car, it's a truck, or it's a 0, it's a 1, it's a 9. And this is the power. Now, we humans don't have to do this anymore. We have to steer that with the architecture, admittedly. So what was once feature engineering, thinking about symmetry and massaging the data, now has been basically coming to something we call architecture, neural architecture search, where you kind of want to have the perfect architectures. Now, the rule of thumb, there are some which are very well known and often used. ResNet 50, for instance, is a so-called gold standard in neural networks, which you use for image recognition. If you are computational moderate, you would have higher ResNets for if you swim a little bit more in computing power, and of course have better performance. But there's something which are residual networks, which Rocco will also address and me later, where you have some skip connections between layers to preserve also something there. But step by step, you have here the basic ingredient now, firstly, as a concrete model that the CNN is working quite well with this structure. And secondly, the idea of deep learning that is not just putting the neurons, but has a very specific way of working with the neurons one by one. How that looks like in an illustration is basically here. There's a website where you can play around. You see, basically, I can paint an image, which is a 7. And here you have the different feature maps step by step. And when you use the, let's say, website, you can click on each of these pixels and see the basically the connections of that. Connecting to the next layer, the next layer, the next layer. You also see the different features in the 7 that are learned, right? Some is a bit more shady. Think about that this is now was trained on many, many different data sets before. So some have done the 7 maybe a bit more, let's say, tough in really, you know, black grayscale, as I would say it, than just soft grayscale and things like that. So we will basically use the learned information to identify this image as a 7. And you will see also in further down the road, you will basically not even identify a 7 anymore, right? So these are features which are just broken, basically these into smaller pieces, and see there's always something common which differentiates us then from the 7. Equally, if you then do the exercise a little bit and go and paint a 0 and paint an 8, you will see quite an overlap, right, in the grayscale points. Hence, there's a probability that you see here also later on. It could be an 8 or a 0, hopefully alluding to the number you have right. You also see that in the end, from these interesting deep learning algorithms, or many of them at least, especially here in CNN, you will find the same structure we had in neural networks before, a dense layer. So here, every neuron is connected to every other neuron, as we had before. But here is weight sharing and feature maps, as we discussed, and this all alluding to a very good performance. We hope. We didn't saw it yet, so let's see. And then our next Python comes to play. Obviously, in deep learning, we just don't add a dense layer, number of classes done. Here we have to do some more work to do a little bit more, and that means thinking about the architecture now that you have seen here as an example, right? Which is, I think, as I remember correctly, AlexNet or a derivation for that. So it's something that, you know, some of these models you can already take and use. They have been used in computer vision, basically benchmarks, and won lots of basically competitions. So they're very good to start from. But if you have a really application, it's good, you know, that like Rocco, he does remote sensing a lot as a PhD of me. So basically he used ResNet and much more elaborate models. But still, that's a good way to start. Hence, also we have to look on the structure here. The beauty, however, is in Keras, it's very similar like we had in the neural networks before, right? So still we have the input model. We say it's sequential in terms of the different layers. We have discussed that we want to have now a convolutional 2D, right? Because our problem was 2D. We have grayscale. So in this sense, if you have a, let's say, RGB image, maybe it's better for do conv 3D. You have a kernel size, thinking about how many of those you want to learn. Padding is something when basically this size you go over for the filter is not fitting. So it fits in basically the data with the supporting padding. Here you have basically the nonlinearity as an activation function, ReLU, right? That is still there basically for each of the different neurons to use to catch nonlinearities. And then do the pooling, which could be max pooling, as I said, strongest signal survive. Also there you have a flexibility. What is your pool size, 2 by 2? How far you go over the, basically, or how many steps with a stride you do over the different images. So lots of these parameters basically are, you know, taken for you given this architecture. But of course, nowadays we are in neural architecture search, rather searching for exactly those parameters to do it better. And here is no secret. Again, the idea is then, of course, copy that layer by layer by layer. And by doing so, we see that basically the 7 will be crunched more into smaller number of features we have seen in the demonstration. So that is all nice. And we learn the feature like we humans do. And then we have a dense layer just to, let's say, learn the signal and then put it to the output probability. But what you also should see in this, and this is also part of your assignment, obviously, so you will play around a little bit with this and learn better than just seeing it on my slides. We have 1.2 million parameters. To recap, we started at 8,000 in the first, right? 8,000 for multi-output perceptron to learn, to process, to compute. Then we have been at 120,000 for a neural network, 2 hidden layers. And now we're at 1.2 million parameters to learn. Of course, it gives us a spatial connectivity and we assume better performance, but there you go with the price of computing time. Hence, clouds and HPC for deep learning really required. And this is basically only a toy problem, and you will see already the big difference if you execute it on CPUs, for instance, versus GPUs and so forth. And then really with Rocco, with distributed deep learning, he's a guy that really uses these 2,000 GPUs or 500 GPUs together. There you really see the big impact of the clouds that you cannot do with laptops. And when you go on, basically now for the source code, many of the same principles stay the same. We still have the Apache 20. Nobody tells us that's the best one, but we want to have it as a benchmark to compare it with the artificial neural network and the multi-output perceptron. We switch a bit. The optimizer atom is usually used more in these models. Validation split is something which we allude to a bit later. It has something to do with, let's say, properly learning and also fighting a bit the, overfitting we discussed in the first part. We have now, of course, no input reshaping to be done. This vectorization is gone, right? We take the image as is. Still, of course, from the input size of the image, we maybe have to adjust it, some of the neural networks. When we do COVID chest X-rays, we cannot take just the chest X-rays. We have to significantly crunch it because we don't have computational capacity to just work on the whole chest X-ray in this type of deep learning architectures. So basically, this is still something which could be done, but still it preserves the spatial connectivity, which is important for us. Then we have training, test set, breaking this down. The idea of still doing normalization is important because we do layer by layer multiplications, etc. So and if you just have integers, it will blow up quickly and you basically are out of the capacity of an integer, for instance. So this is very important too. And this is a little bit just for printing and some of the train and test samples that you will see when you do the assignment 2 and so on. We can then go on and we'll learn it basically also in the assignment. And of course, here comes our surprise. Not really a surprise. We thought about it a bit already that it could be maybe close to 100%, but here we pay the price of some of those which are basically unlearnable even for a human, right? So, I mean, this is something where even we humans would have problems of recognizing this number or determine always it's a 7 or a 1 or something like this. So we did this in 20 epochs and have learned 1.2 million parameters. So you will explore that the output in perceptron or multi-output perceptron, the artificial neural network, simple in computing. When we go to deep learning, 1.2 million, you pay the price for the time of computing. So what else left? I think running this basically will show you in the assignment a little bit also, that you shouldn't use CPUs. Secondly, it means, of course, you need the right environment. And that means also that in the Google Collaboratory, as I said, you have just one GPU that's limited. Hence, we will talk about distributed deep learning in one of the subsequent lectures. And that's really all I think I wanted to leave here for you. I have a little bit longer video now for you to summarize a bit, but also motivating a bit that machine learning doesn't stop here. So what we didn't cover is really overfitting to a significant degree, which you should do in the machine learning course at least for 2 or 3 lectures. Combating it with regularization techniques. In neural networks, you would do weight drop or weight decay. So it means that every now you just, basically don't compute one of these weights. Leave them out, 20%, right? Every run is a validation, for instance, a regularization parameter, weight drop. If You don't consider them. By this, the model gets a bit smoother and the video catches this a little bit. Hence, a whole machine learning course is just starting at that part when you really want to go to practice. In other words, you could also do not machine learning unless very naively if you don't do regularization validation. Both always have to be part of the story. So let's go a little bit to the summary video before we then come to the third course hours for questions.
Dear fellow scholars, this is 2-minute papers with Károly Zsolnai Fehér. In machine learning, we often encounter classification problems where we have to decide whether an image depicts a dog or a cat. We'll have an intuitive but simplified example where we imagine that the red dots represent dogs and the green ones are the cats. We first start learning on a training set, which means that we get a bunch of images that are points on this plane, and from these points we try to paint the parts of the plane red and green. This way we can specify which regions correspond to the concept of dogs and cats. And after that, we'll get new points that we don't know anything about, and we'll ask the algorithm, for instance a neural network, to classify these unknown images so it tells us whether it thinks that it is a dog or a cat. This is what we call a test set. We have had lots of fun with neural networks and deep learning in previous 2-minute papers episodes. I've put some links in the description box, check them out. In this example, it is reasonably easy to tell that the reds roughly correspond to the left and greens to the right. However, if we just jumped on the deep learning hype train and don't know much about neural networks, we may get extremely poor results like this. What we see here is the problem of overfitting. Overfitting means that our beloved neural network does not learn the concept of dogs or cats, it just tries to adapt as much as possible to the training set. As an intuition, think of poorly made real-life exams. We have a textbook where we can practice with exercises, so this textbook is our training set. Our test set is the exam. The goal is to learn from the textbook and obtain knowledge that proves to be useful at the exam. Overfitting means that we simply memorize parts of the textbook instead of obtaining real knowledge. If you are on page 5 and you see a bus, then the right answer is B. Memorizing patterns like this is not real learning. The worst case is if the exam questions are also from the textbook, because you can get a great grade just by overfitting. So this kind of overfitting has been a big looming problem in many education systems. Now the question is, which kind of neural network do we want? Something that works like a lazy student, or one that can learn many complicated concepts? If we are aiming for the latter, we have to combat overfitting, which is the bane of so many machine learning techniques. Now, there's several ways of doing that, but today we're going to talk about one possible solution by the name L1 and L2 regularization. The intuition of our problem is that the deeper and bigger neural networks we train, the more potent they are, but at the same time, they get more prone to overfitting. The smarter the student is, the more patterns he can memorize. One solution is to hurl a smaller neural network at the problem. If this smaller version is powerful enough to take on the problem, we're good. A student who cannot afford to memorize all the examples is forced to learn the actual underlying concepts. However, it is very possible that this smaller neural network is not powerful enough to solve the problem, so we need to use a bigger one. But bigger network, more overfitting. Damn, so what do we do? And here is where L1 and L2 regularization comes to save the day. It is a tool to favor simpler models instead of complicated ones. The idea is that the simpler the model is, the better it transfers the textbook knowledge to the exam, and that's exactly what we're looking for. Here you see images of the same network with different regularization strengths. The first one barely helps anything, and as you can see, overfitting is still rampant. With a stronger L2 regularization, you see that the model is simplified substantially and is likely to perform better on the exam. However, if we add more regularization, it might be that we simplify the model too much, and it is almost the same as a smaller neural network that is not powerful enough to grasp the underlying concepts of the exam. Keep your neural network as simple as possible, but not simpler. One has to find the right balance, which is an art by itself, and it shows that training deep neural networks takes a bit of expertise. It is more than just a plug-and-play tool that solves every problem by magic. If you want to play with the neural networks you've seen in this video, just click on the link in the description box. I hope you'll have at least as much fun with it as I had. Thanks for watching and for your generous support, and I'll see you next time.
funded by 2 papers, which was a 4-minute paper, but I think it has nice graphics, so I think it was hopefully helpful. Just again, the warning, what you learn here in the course is just really the scratch of the iceberg. So you have to learn a lot of more concepts, statistical learning theory a little bit, and regularization, as you have seen, is basically every time part of the game, plus validation, which basically stands for model selection in a very specific way. So lots of interesting hidden assets in machine learning that we cannot really talk about much in the course, because I also want to talk about cloud computing. So that's what we do in lecture 7, the next time, where we connect it now to GPUs, why that's important, where clouds make a difference in this tensor flows, you basically have already seen indirectly here today. And we close here for this lecture today, and see you in lecture 7 then next time.